start? Okay. So good morning to all. So today we will be looking at some of the applications of shock waves. So therefore, let us proceed. So let us first start with where we stopped last time. Okay. Okay. So let us recollect what happened in the last class. Look here. So we looked at how sound waves were classified, and so after classification, after knowing how the sound waves were classified, we stopped at that point. Okay, so therefore today we will move on to the description of shock waves, then the law of basic conservation laws, and some of the applications of shock waves. Okay, so therefore let us quickly recollect what happened in the previous class. Look here. So how are the sound waves classified? First we came to know about the idea of Mach number. What is Mach number defined as? In aerodynamics, always the speed of an object is compared with the speed of sound in a given medium. Okay. Yeah. So in aerodynamics, the speed of an object is always compared with the speed of sound in a given medium. Therefore, Mach number m is defined as the ratio of speed of an object to the speed of sound in a given medium. Okay. So next after that we saw how sound waves were classified. So how the sound waves are classified? So look here, and we also know about this. The expression for the speed of sound in a medium is given as per Newton's formula as A is equal to square root of gamma into RT. Okay, and where the symbol gamma and R have their own usual physical significance or usual meaning. Okay, next. So how are the sound waves classified? Sound waves are classified as acoustic waves, ultrasonic waves, subsonic waves, supersonic waves, and hypersonic waves. So in the case of acoustic waves and ultrasonic waves, what we know, the amplitude of vibration is going to be small. Amplitude of vibration is going to be very small. And in the case of acoustic waves, the frequency range is going to be between 20 hertz to 20,000 hertz, which are audible to human ear. On the other hand, in the case of ultrasonic waves, those pressure waves or those mechanical waves, they will have sound wave, they will have frequency which is beyond 20,000 hertz, which is not audible to human ear. Okay, and in both of these instances, those sound waves will move at a speed of around 330 meters per second, roughly at standard temperature and pressure in air. Next, what was subsonic waves? So subsonic waves are the mechanical waves described by an object when it is moving with a fluid, that is, it is moving in a fluid where the speed of an object is less when compared to speed of sound in a given medium. Okay, so yeah, therefore in the case of subsonic waves, what happens? So sound vibrations are going to be moving ahead of the object. Okay, next, this is the diagram. So I'll just come to this. Now what are supersonic waves? So supersonic waves are the mechanical waves produced by objects that is moving with a speed that is greater than the speed of sound in a given medium. That is, V is greater than A, or the Mach number m is going to be greater than 1. In this case, what will happen? The sound emitted by the object is going to be behind the object. It will move behind the object. Okay, how does this synchronize to? Okay, so therefore let us look at this diagram. Okay, so take this. Okay, so just look here. It's the recollection, it's a recapitulation of what went in the earlier class. So what is that? If the object is moving with a speed which is less than the speed of sound in a given medium, that is, m is Mach number m is less than 1. If that happens to be less than 1, if Mach number is less than 1, in that case, what will happen? Can you see here? So this is a circle. This is a sound vibration that is expanding as time lapses, and this is the What is this? This is nothing but an aircraft which is moving towards left. And can you see here? So if the Mach number is less than 1, then part of the circle, part of that circle, part of the circle or part of those sound vibrations, they are lying before the object. Can you see here? For example, 4 circles or 4 arcs of circles are there before the object. Therefore, if an object is moving at a speed which is less than the speed of sound in a given medium, then the sound waves are going to be, sound vibrations are going to be before the object. Okay. On the other hand, if an object is moving with a speed where the Mach number is greater than 1, if the Mach number is greater than 1, then what will happen? All the sound vibrations are going to be behind the object. They are going to be behind the object, and this we call it as what? Supersonic waves. Okay. So therefore, in this diagram, all the 3 cases are captured. So this is the case of subsonic waves, where the sound waves are before the object. This is supersonic waves, where the sound waves are behind the object. And this is if an object is moving with a speed which is equal to the speed of sound in a given medium. That is, if Mach number is equal to 1, then can you see here the sound vibrations? Can you see in this region? The sound vibrations will stop being before the object. Okay. So the sound vibrations are going to stop but being before the object. Okay. Therefore, you can just see here that the expanding expanding envelope of the circle. Okay. So sound vibrations are just tangential to the plane. Okay. This straight line is tangential to the plane at this point. Okay. So therefore, this is done. Next, we'll look at hypersonic waves. We'll next look at the hypersonic waves. Okay, so what are hypersonic waves? Yeah, it's done. So what are hypersonic waves? So supersonic waves is done. Next, what is Mach cone and Mach angle? So again, let us recollect this concept. What is Mach cone and Mach angle? I'll undo all these things. Okay, I'll just focus only on this figure. Okay, so what is Mach cone? Okay, I'll just quickly define it. What is this? Look here. If the locus of direct common tangent, the locus of direct common tangent is going to be a straight line. Okay, so this is a common tangent for all the expanding sound waves that is there behind the object. So now, who wants to join now? Yeah. Now what is Mach cone? So if I draw this direct common tangent, all sound vibrations are confined to be within this cone. Such a cone we call it as what? Mach cone. Okay. So this we call it as what? Mach cone. Okay. Can you see here? All the sound vibrations are confined to be within this cone. This I call it as Mach cone. Next, what is Mach angle? If I draw the axis of the cone by a dotted line. So Mach angle is nothing but what? Is the angle made by the direct common tangent with the axis of the cone, which is generally denoted as mu. So what is this angle? This angle we call it as Mach angle. Okay, this angle we call it as Mach angle. This angle is called as Mach angle. Okay, so shall I highlight? Yeah, can you see here? This is called Mach angle. This is called Mach angle. Okay, so this will be related to the Mach number by the relation sin mu is equal to 1 by m. So this is done. Next, so these are what? These are just the recapitulation of what happened in the previous class. Okay, next, what are hypersonic waves? Hypersonic waves are those sound vibrations produced by an object that is moving with a speed which is greater than 5 times the speed of sound in a given medium, or Mach number is going to be greater than 1. So this locus, can you see here? This locus is going to be what? An hyperbola. all sound vibrations that are confined to be within this cone, we call it as hypercone, and so on. Okay, this is done. Next we'll look at the shock waves. Okay, so whatever we have done so far is the last 8 minutes is simply a recapitulation of what went in the previous class. Now we will look at the shock waves and its applications. Now what are shock waves? Before I do that, I will just show you the following video. Okay, so let me close this. Okay, so look here, this is a video in which a volcano was erupting near a seashore. Okay, so when the volcanic eruption occurred, shock waves were produced. Okay, this is an instance where a volcano was erupting in a seashore near New Guyana, which is West Indies. Okay, and you see that it produces a shock wave. So it will take nearly 2 or 3. It will take only if we play this for say 2, 3 or 4 times, we'll come recognize what is a shock wave. Okay, therefore let us play this. Okay, can you see here? This is the spot where the volcanic eruption is about to occur. Okay, now look here. Generally, if a volcano erupts or if an explosion occurs, we know that dust and flame or smoke is going to come out. Okay, so when an explosion occurs, smoke, dust, all these things will come out. But when I'm talking about shock waves, I'm talking about those things apart from these flames, smokes, and so on. Okay, what does that mean? So look here. So let me play this for the initial 10 seconds and then I'll describe. Okay, concentrate what happens in this region, in the topmost region. Okay, concentrate what happens in the topmost region here. Okay, let us play this. Okay, can you see? Okay, these are dust and smoke. I'm not referring to that. Somewhere on top of it, a white color cloud is going to expand. Okay, just like what you see in ghost movies. Okay, just see here once again. I'll replay the video. So you'll see that a white layer of clouds will expand or move away from this. That we call it as shock waves. Just now observe. Okay, focus particularly on this region. Here, something went.
Watch out for the shock, it's coming.
Focus on top.
Watch out for the shock, it's coming.
Okay, can you see some clouds are just expanding? Okay, just like a glass. Once again, last time I'll play. Look here, already there are white clouds. We are not referring to those white. Already there are white clouds there. We are not referring to those clouds, nor we are referring to the dust or the flame that is coming out of this volcanic zone. What we are referring to is something that is happening in the sky at a far off distance from here. So you see that will expand. I'll replay the video again. So some white cloud will expand somewhere here. Okay, and there will be no physical contact between that and this point. Okay, so therefore it happens in air.
Watch out for the shock, it's coming.
So that is shock wave. Okay, so I think I'll stop playing this video. This is enough. Okay, yeah. Now let us get into the technical definition of shock waves. Okay, what is shock wave? Okay, what is shock wave? Look here, any fluid that is moving at a supersonic speed, it will give rise to shock wave. Okay, so in my first class itself I showed if a jet moves at a very high speed, it produces shock waves which is going to be behind the object. So the shock waves are produced in nature during earthquake and when a thundering occurs during rainy season. Okay, now what is the technical definition of a shock wave? A shock wave is a surface that manifests as a discontinuity in a fluid in which it is propagating at a supersonic speed. Okay, so what does that mean? Once again we will tell what is the definition. What is the definition of shock wave? So what is the technical definition? A shock wave is a surface that manifests as a surface of discontinuity in the fluid in which it is moving at a supersonic speed. Okay, so it is a surface of discontinuity. What does that mean? What does that mean? Once again, let us look at what happened in the case of motion of a ship. Okay, if I look at the motion of a ship in water. Okay, look here. This is the motion of a ship. Okay, can you see here? This is the ship which is moving in water. Okay, now look here. I will focus on following. Okay, this is the ship which was moving in water. Okay, suppose I use a yellow color line. Can you see here? I'll focus only on this border of this expanding water waves. Okay, can you see here? This border of this expanding water waves. It's a border. It's expanding with the time. Okay, can you see here? This is the border which we call it as the surface of discontinuity. Okay, so this will be a small region. This will be a small region during which the gas present in the fluid or the water in the medium is going to be compressed. Okay, can you see here in this border line? This is the border line. In this border line only what happens? The sound waves will be compressed to the medium will be compressed to a very high value, which we call it as surface of discontinuity. Therefore, let us look at the technical definition of a shock wave. What is the technical definition of a shock wave? So I'll close this. Okay, what is the technical definition of a shock wave? Look here, shock wave is defined as what? It is the, so what is a shock wave? It is the surface of discontinuity. It is defined as a surface of discontinuity that manifests as an object is moving at a supersonic speed in the given fluid. Okay, what does that mean? What does that mean is, can you see in this figure? It is this tangent. That is, this tangent is there, no? The locus of this direct common tangent. So this is the region where the gas is going to be compressed to a very high value. And this region we call it as what? This line, we call it as what? The surface of discontinuity, or it is a shock wave. And what will be the thickness of the shock wave? The thickness of this shock wave is going to be just a few micrometers. Okay, what does that mean? What does that mean? Thickness is going to be few micrometers. Micrometers means it is going to be of the order of 10⁻⁶ meters. So within this region, what happens? the gas or the fluid will be subjected to high value of compression. Okay, as I showed here in the case of water, this is the border in which the sound waves will be compressed to a high value. Then what happens? Once again, what is a shock wave? A shock wave is a surface that manifests as a surface of discontinuity in a fluid in which an object is moving at a supersonic speed. Okay, so next, what do you mean by discontinuity? Look here, in calculus, discontinuity means left hand limit is not equal to right hand limit. So what does that mean? What does that mean is, if I just focus only on this small region, which is if I focus only on this small region where that direct common tangent is there, right? If I denote the pressure and temperature by say P1, then temperature as T1 and the density of gas as ρ1, you will see that the density, pressure and temperature in this region is going to be very high when compared to what you see in the atmosphere. Therefore, P2 will be very much small when compared to P1. T2 is going to be very small when compared to T1, and ρ2 will be small when compared to ρ1. Okay, I'll put it in simple words. In this region, what happens? In the region, the density, temperature and pressure of the gas is going to be very high. Okay, so this is done. Next, let us move on to how a shock waves are produced in nature. Okay, this is done. Next, so this is what I showed in the previous class also. If a jet is moving, then the shock waves are produced behind the object. Next, how are shock waves produced? Shock waves can be produced by the sudden dissipation of mechanical energy in a medium enclosed in a small space. Okay, for example, can you see here, if you simply clap your hands, so if you clap your hands, what will happen? The air will be made to expand suddenly. Suddenly means suddenly in an adiabatic condition. Okay, so shock waves can be produced by making the medium to expand suddenly or to compress suddenly. Okay, so whether you expand the medium suddenly adiabatically or you compress it adiabatically, that leads to the formation of shock waves. Okay, next, within the shock wave, the pressure, temperature and density of the gas will undergo instantaneous changes. That is what I was referring to in this figure. Okay, in this figure, what happens? Can you see here? So if I consider the locus of direct common tangent, if I consider the locus of direct common tangent, okay, if I consider the locus of direct common tangent, what is the thickness of this common tangent is going to be few micrometers. Within that region, you will see that the gas is subjected to high value of compression. Hence, pressure is going to be high, temperature is going to be high, and density of gases are going to be high in this line of discontinuity. It is going to be very high in this line of discontinuity. Okay, so this is what you mean by this definition or this sentence. Okay, next, a shock wave is characterized by sudden increase in pressure, temperature and density of the gas through which it is propagating. Okay, next, what is sonic boom? A shock wave by itself cannot be heard. What we hear is generally if a bomb explodes. Okay, if a bomb explodes, what you hear is the sound of this bomb. Okay, so if a bomb explodes, how do you hear the sound? It's going to be bum, bum, ghum. So that bomb sound is there, no? That is what we call it as boom, boom, bum. Correct? Therefore, what is sonic boom? What is sonic boom? Okay, what is a sonic boom? A shock wave by itself cannot be heard. What we hear is the booming sound as the velocity of the object increases or as it exceeds the speed of sound in a given medium. So velocity increases means what? If a jet accelerates and if its speed exceeds the speed of sound, then those sonic boom or the sound vibrations are heard, even if the plane has receded from us over a very large distance. Okay. Next, how many types of shock waves are there? There are two types of shock waves. They are strong shock waves and weak shock waves. In the case of strong shock waves, what happens? The compressed regions will possess a very high value of pressure and temperature. For example, shock waves that are produced during lightning or thunder or during nuclear explosion, they are the examples for strong shock waves. Now, what are weak shock waves? So these are the waves that are characterized by the object that is produced when they are moving with a Mach number which is less than 1. Okay, if the speed of an object is less than 1, then those sound vibrations or mechanical waves that are produced by an object, they are going to be they are labeled as weak shock waves. And what is the example for that? The example for that include the explosion of cracker and the bursting of an automobile tire. Okay, in all these instances, what happens? The compressed region will be subjected to low value of pressure and temperature. Hence, we call it as weak shock wave. On the other hand, if an volcanic eruption occurs, the compressed region will be subjected to high value of temperature and pressure. Okay, next. So what are the three conservation laws? So there are three conservation laws. They are the law of conservation of mass, law of conservation of momentum, and the law of conservation of energy. So we all know about the law of conservation of energy and momentum when we studied about elastic collisions in physics, right? So what is law of conservation of energy? Take this. What is the law of conservation of energy? So in an isolated system, the total energy of the closest of an isolated system will remain constant even if there are changes that are occurring within the system. So in the case of law of conservation of energy, so any isolated system, if the total energy of the system happens to be constant, then this law we call it as what? Law of conservation of energy. We call it as law of conservation of energy. Next, what is law of conservation of momentum? So if a system of particles, if a collection of particles, if they collide, what happens? The total momentum before collision will be equal to total momentum after collision, or the total momentum of this system is going to be constant. So this we call it as what? Law of conservation of momentum. Next, what is law of conservation of mass? So in this case, what happens? The total mass of any isolated or closed system will remain constant even if there happen to be changes in the physical or chemical reactions that may occur within the system. Okay, so these are the three basic laws. So which are the three basic laws? One is the law of conservation of mass, law of conservation of momentum, and the law of conservation of energy. Okay, next we will look at the applications of shock waves. Okay, we will look at the applications of shock waves. Okay, so Reddy shock tube, the details of Reddy shock tube that we will discuss in the next class. So you can produce shock waves in the lab by using this setup, which we call it as Reddy shock tube. Okay, next. So what are the various applications of shock waves? Okay, look here. So shock waves are used in there are several applications. Okay, it is used in medicine, it is used by a carpenter. So it is used in mechanical waves, it is used in aerospace. So therefore, these are few applications. Okay, first, it is used to know the cell information. Next, it is used to preserve. It is used in the preservation of wood in the industries. Next, shock waves are used in pencil industry. It is also used to treat persons who are having kidney stone. Then it is used in the treatment of dry bore wells. Then shock wave is also used in needleless drug delivery. Okay, so we will take up this application one by one. First, so cell information. So what is this? Okay. Okay, so look here. So what is that? Look here, for example. So this finds lot of applications in biology and biotechnology. Okay, in medical field this is important, in biophysics or biological related applications. Okay, so generally, for example, let us again take the example of our coronavirus outbreak. Okay, so first what happened? Okay, initially what happened in December, say around December 20th 2019. Okay, between December 15 to December 31st 2019, around 1.5 years back. Okay, what was observed was, so there were cases of some 44 patients. All of them had same symptoms, that is they had a breathing problem. Okay, they had breathing problem. Some of the doctors who attended the cases of those 44 patients in Wuhan's medical center, so what they found was it is the same pattern. It's the same pattern found in in all those set of 44 people, but they do not know what is happening. So that problem or that outbreak was initially labeled as what? Pneumonia of unknown cause. Okay, or pneumonia of unknown origin. Okay, so some of the experienced doctors who were attending the patients during that time, they guessed that a new kind of virus is roaming around. They called it as a new kind of SARS kind of virus is moving around. Okay, that is what they guessed. And what happened? That guesswork happened to be true. Okay, so therefore what later came to, what people came to know, so after somewhere around January 10th to January 15th, so until that point it was known that there were around 6 coronaviruses that can infect a person, infect human beings, including the coronavirus that leads to common cold. Okay, and during that time what they found, there was a seventh new coronavirus that is infecting a person, that is leading to this human to human transmission, and hence that is leading to pneumonia or breathing problems in exceptional cases or in extreme cases. So that people called as what? SARS-CoV-2 or COVID-19. Okay, so how is that done? Okay, the what is how is that done? The bottom line is the same, the approach is same. What you do, you take a sample of a blood, or you take a sample of cell from the tissue of a person, and then you will use a microscope to analyze those cells, or you will try to analyze the virus that gave rise to these symptoms. Okay, so likewise, so knowing the cell information is a very important, it's a very important technique, or it's a very important very important in knowing many properties or many things related to the disease. Okay, sometimes in the case of new disease as well it will be used. Okay, this is, so therefore how do you know the cell information? Obviously what you do, you take part of the cell from the tissue of a person or a part of a blood sample from a person, and you start analyzing them under a microscope. Now how do you know the cell information? In order to know the information about a cell is going, the size of a cell is only going to be anywhere between few micrometers to few nanometers. Okay, so in order to extract the information about a cell, some molecules or some DNA or RNA whose properties you know, you have to push it inside the cell. Okay, based on this DNA there will be changes that will appear from the cell. So from that changes we can find in lot of information about the cell. Therefore what is the key part? You have a blood sample, or you have a sample of cells collected from the tissue of a person. So in order to extract the cell information, what we have to do, you have to pass that, you have to push DNA inside the cell. Now, where are we? Yeah, you have to push DNA inside a cell, right? So therefore, now look here. So now question is, how fastly can you push the DNA inside the cell? That's a question. How fastly or how quickly you can do that? That's a question. Therefore, what we do, look here. So you take your cell and it will be, say, immersed in a solution containing DNA of interest. So next what we do, by passing shock waves of appropriate strength. What do you mean by shock wave? Simple. Make the medium to compress suddenly, or make the medium or make the fluid to expand suddenly, adiabatically. That will give rise to what? High pressure and high temperature and high density in the compressed region. Okay. So by pushing, so shock wave is simply like a mini explosion. Okay. By passing shock wave of appropriate strength, DNA can be pushed inside a cell. And what is the advantage of this? The advantage of this is the functionality of the DNA will not be affected by the impact of shock waves. Okay. Therefore, the DNA that are pushed inside the cell by this fast mechanism, so they will be able to reveal or give us, shed light into lot about the information about a cell. So therefore, what is the crux here? Crux here is, by using shock wave or by passing shock wave, DNA can be pushed inside the cell, and these DNA, their functionality or their properties are not affected by on passing shock waves. Therefore, cell informations, the information about the cell can be extracted without any hassle. So this has lot of applications in biology. Okay, biological applications you find. Next, the second application being in the preservation of wood. Okay, preservation of wood. So I think now time is 11:30. Let me look. Okay, look here. For example, I go to okay, can you see here in this figure? See, there are bugs which can eat wood. Okay, so these are bugs or mites that can eat wood. Okay, even if the wood is exposed to microbes, microbes can eat the wood, and hence it will reduce the quality of wood. Can you see in this figure? Can you see in this figure? There are few bugs which are eating the wood. Sometimes what will happen is, in a forest or in a garden, you will see that the entire tree will be it would have been infested by this bugs. Okay, now let me come to this point. Okay, I think this is clear. There are bugs or mites that are going to eat the wood. Okay, look here, this is clear. Now let me go. Okay, the problem. So first let us identify, and the part is how to solve it in a elegant way. Okay, now look here. Yeah, look here. See, there are few bugs, or there are few mites, bugs or mites, mites. Okay, there are few insects or bugs. Okay, and look here, in your home, if this bug comes to one of the window or one of the furniture, it can easily start moving around, and it will start eating the other furnitures present in your home, including doors. Okay, now the problem is the following. What is that? There are few bugs or mites or microbes which will eat the wood. So if they eat the wood, what will happen? The the quality of the wood is going to come down. And hence, if you make a furniture out of it, even a small person, even if he sits, it will break immediately. Okay. Now how do we overcome, or how do we increase the lifetime of an wood so that the bugs don't eat it? So that is a question. So how is that done? By making use of few chemical preservatives. Okay. Generally, in order to avoid this, what people do what painters do is they use turpentine and paint. Okay. If they use turpentine oil and paint, then these bugs will not come. Okay. That is one way. Next is what? By using chemical preservatives. Okay. Look here. See, in order to increase, see, for example, if you take food, so the food that is cooked now, within next day morning or afternoon, it will decay or it will deteriorate, right? So in order to avoid food from deteriorating immediately within a day or two, what we do is sometimes we make use of chemical preservatives. So if you use chemical preservatives, of course, it's all artificial that you see while we make fast food. So when if you inject chemical preservatives in food, what happens? The food will not deteriorate even after 4 or 5 days. So even after 4 or 5 days, the food is going to be in a condition by which which is conducive for us to eat. Likewise, in order to avoid the bugs, or mites or the microbes from destroying our wood, what we have to do? We have to use chemical preservatives. If I look here, yeah, close this, yes. Okay, so what is the second application? Look here, by using shock waves. So chemical preservatives in the form of solutions could be pushed into the interior of wood samples such as bamboo. Okay, what do we mean? Okay, so look here, first you consider for instance a small piece of bamboo. Okay, so you take this bamboo and put it in a solution consisting of chemical preservatives. So chemical preservatives will be in the form of a solution. Okay, now if you wait for these chemical preservatives to penetrate or get inside bamboo naturally, this will take around 15 to 20 days. Once again, I'll repeat. So in order to make sure that the chemical preservatives will penetrate the interior of the wood naturally, it will take minimum 10 to 15 days. Now next question is, how can you push these chemical preservatives inside the wood fastly? That's a question. So how is that done? By using shock waves. So therefore, what does that mean? By using shock waves, chemical preservatives in the form of solutions could be pushed into the interior of the wood samples such as bamboo. So this method makes the process of introduction of preservatives into the wood much faster and more efficient. So this in turn will enable the wood to withstand microbial attacks. So by this method, what is the advantage? The lifetime of ordinary bamboo and softwood, they can be increased substantially. So therefore, what is the key? By using shock waves, you can suddenly push these chemical preservatives inside the wood and hence increase the quality of the wood and also its lifetime by few years. Okay, this is the second application. Next, the third application. The third application of shockwave is, it is used in pencil industry, then in kidney stone treatment, and in shockwave assisted needleless drug delivery. Okay, so these 4 applications along with construction and working of ready shock tube, that will take up in our next class.